Hi, this is Jason McIntosh. This video is going to try to be a short introduction to Aries, but all these videos seem to take a bit longer than I anticipate, so bear with me. As this slide says, Aries is a collection of tools for doing acoustic design and measurement. Aries is designed around a series of modules. Rather than having a separate program performing each function, Aries has a single interface to the program that implements many features. Each main group of features is collected into what's called a module. SATI currently offers 4 modules for sale. The main one and the central focus of Aries is a linear lumped element modeler. There's also a nonlinear lumped element modeler, a frequency response measurement module, and finally a coordinate mapper. The coordinate mapper is a useful tool but not specifically for acoustics. Also, Aries is a Windows program. It's not available on any other platform. If you're using a Mac, you'll need to use a Windows emulator of some sort. The modeler is the central focus of Aries, and our output, that is our goal, is a design that we can be happy with. A variety of inputs go into that modeler to help you in your design process. Speaker parameters are a common one. Teal small speaker parameters are usually available from the vendor. These models in Aries are really a connection of devices with various acoustical impedances, driven by either a speaker or an external pressure source that has a wavefront arriving at a microphone. All these elements have some kind of acoustical impedance, and occasionally there's a need to model or measure these impedances outside of Aries, and so Aries has the capability of importing acoustic impedances from other sources. A very typical use for SATI is to measure the impedance of a SATI mesh or membrane and then bring that into the model. We can do that for you if you work with us. Then finally, the frequency response measurements typically give the actual response from a device that's been built up, and you'll use that to compare it to the model and see how well your model did predicting the output. So the design approach is shown here. Initially, when you start out with a new project, you will typically build an Aries model where you work with the speaker you have in mind or microphone you have in mind. You'll include various volumes and ports that you have enough room for in your design until you reach a point where you feel like you have a desirable acoustic response from your design. You'll then typically, using 3D printing techniques, build a mechanical model of your design and measure the response. You'll then take that experimentally measured response, import it back into the model, and you can see how the measurements and the models differ from each other. It's quite common for the model and the measurements to be off, and it's not necessarily the modeler or the experimental measurements that are wrong. It's just that you need to figure out why they're different and eventually change your design so that you arrive at your final desired response. A typical reason for differences between the model and measured response might be you have a pressure-sensitive adhesive that you're using to create a seal, but that adhesive failed and you have a leak through it. Or perhaps you're using a speaker whose higher order modal responses aren't captured by Teal small parameters, and so you have a difference for that reason. So there are good reasons for having a difference between your model and your measurement, but what you typically want to do is correlate them, try to adjust your model so it matches the experimental results as much as possible, or that you understand why your experimental results are different. Once you correlate your model to your experiment, you then typically decide what direction you want to take your design to get the desired response you're after. And that's where you use the model to help you take the next step in this iterative process. You'll build a new 3D model, measure its response, correlate it to the model again, and iterate back and forth probably a few more times until you arrive at a final optimized design. Now, it's been my experience that this model/measurement approach gets you to a final design much quicker than if you just relied upon a model approach or if you just relied upon an experimental approach. So the modeler is meant to be fast and complement the experimental approach well. Typically, an ARES model is solved in less than a second, so you can run hundreds and hundreds of simulations in an afternoon, and then the next day you can build an experimental realization of your model and see how well they correlate. So the model and the measurement are meant to kind of run at the same time scale. Here's an example of a linear modeler model. You have a variety of graphical icons that you can select and drag around and connect together in any arbitrary topology. You will solve for this equivalent acoustic circuit and then generate output graphs that show you what's going on in here. Very typically, you're going to look at pressure at the output, at where you want to generate the response from your speaker, but you can also go in and look at the velocity and acoustical impedances at various points in your design. The linear modeler also lets you do mathematical operations on all these quantities so that you can compute whatever metric you want. You can do plots of magnitude, real and imaginary quantities, and a variety of phase plots are available. And you can import and export data through the clipboard quite easily. So this is meant to be a design tool that is easy to use and doesn't present a great burden to you in getting your work done. This slide shows all the elements available in the linear modeler. The elements are divided into 4 groups. The electrical elements have a white background, the mechanical elements have a green background, and the acoustical elements have a blue background. There are some thermal elements, but these aren't coupled into the other parts of the modeler. I almost hate showing the thermal elements since they're not terribly useful at this point, but if I get a good thermal model for a speaker one day, it would be a good thing to tie in the thermal speaker model with the thermal elements, but that doesn't exist yet. Then finally, there are some miscellaneous elements that don't quite fit into any of these groups. The most common one you'll use is the graph element. This slide shows the screen capture for the nonlinear modeler. The nonlinear modeler is used to predict the THD of a particular design. THD comes from nonlinear mechanisms in your components. ARES currently uses nonlinear behavior of the speaker and nonlinear behavior of the SADI acoustic meshes. Unlike the linear modeler, the nonlinear modeler uses a fixed topology. So you can't add or subtract any of these elements. This topology with a rear volume, a front volume, a port, these are fixed. You can't change any of them. It does have 2 topologies you can choose from, a smaller topology and a larger topology, but these are the only 2 topologies you have to choose from. It's particularly useful to understand where your distortion is coming from, how much distortion you can expect to be coming from your speaker, how much distortion you can expect to be coming from the mesh, what frequencies those distortion mechanisms are occurring at, and what you can do to the volumes in the ports to minimize those distortion effects. The frequency response module uses Windows sound cards to perform 2-channel transfer function measurements. Since it uses just standard Windows sound cards, it's very inexpensive. There's very little additional hardware you need to buy. This picture is showing an external USB sound card that's connected to a calibrator. The calibrator allows you to get calibrated inputs from your sound card. Once you've performed various measurements, you can compute a variety of metrics. It'll compute the total harmonic distortion. You can select what harmonics you want the THD to be computed for. It also computes some telephony metrics such as receive loudness rating, send loudness rating, and the echo measurement. You can perform measurements using a fixed output signal level, or you can tell it, I want a fixed input level. So for instance, you want the signal level at a microphone to be 94 dB. You can tell Ares, adjust the output until you get 94 dB at the input and do the measurement at that level. As with the linear modeler, you can do math operations on the data once you collect them. And the data from the frequency response module easily exports and imports the linear modeler. So you can compare your measured responses with your model expectations. Finally, the coordinate mapper module is a simple module that imports an image such as a JPEG image and allows you to establish a set of coordinates, XY coordinates, with whatever's in that image. If it's a graph like this, it's fairly easy to establish the coordinates. But you could bring in a picture of a phone or something, and you could establish a X and Y extent of that picture, and pick off coordinates from inside of that image that you brought in. In this case, I brought in the image of a frequency response. I selected various points along the curve, which are recorded here in the pane on the left, and now I can copy this data to the clipboard, paste it into the linear modeler, and easily compare my measured data, which I only had on a graph, to what the modeler is predicting, and I can get a good, quick, easy comparison between measurements and experiments that way. So far we've just talked about Ares with a series of slides. I'm now going to run Ares and bring it into our display area here and build a quick model just so that you see how it works. So when you run Ares, you get a blank slate here. The various modules available are under the New Module menu. So I'm going to go down here and I'm going to create a modeler. This is the linear modeler. When I create this linear modeler, it adds a new module to the modules menu. Right now, by default, it's called module 1, and it's identifying it as a modeler module. I can rename that if I'd like to my first model. And if I go back to the modeler modules, you can see that it's now called my first model. If I create another module, let's say I create a coordinate mapper module, it gets added to this module list, and you can have any number of modules you want. When you save your Ares file, all of the model instances get saved to that one Ares file. So you can have a variety of measurements, models, coordinate mapper results, all in one Ares file to help you keep your design files together. And you're not limited to just one type of module here. So if I go over and create another modeler module, I've got 2 modeler modules and 1 coordinate mapper module. I'm going to go ahead and go back to the first one. Now I'm going to build a simple, quick little radiating speaker model here. Between the 2 pipes, I've got my specific modeler module menu. I'm going to create a speaker. I'm going to create a radiation element. I'm going to go ahead and connect that up to the back of the speaker. I can duplicate an element by right-clicking on it and selecting duplicate, so I don't have to go to the menu all the time if I've already got that element in my model. I need to drive that speaker with something. So I'm going to select a voltage source, and you have to have an acoustical, or you have to have an electrical ground reference for electrical elements. So here's my simple little speaker radiating from a baffle model, and I'm going to go ahead and solve it. When I click Calc, it's going to run through the frequencies here. It's going to be pretty fast. So boom, it computed 200 frequencies for us. To go in and view what's going on, you create a graph element that's in the miscellaneous menu. This is how you get that information inside the model. So typically you'll put a connector on the node that you want to look at. When I created that graph element, this window was created. This graph window was created. So I'm going to drag that over in our display area. And here we see our expected output of our speaker for this very simple model here. So the speaker has very little, essentially doesn't have any resonance to it. The response near its resonance is flat, pretty much flat at high frequencies and then dropping off at low frequencies. You can copy that result into buffer A, and now I'm going to go to the speaker, and just for fun I'm going to reduce the damping. So instead of a mechanical damping of 0.3, which is realizing a Q of about 0.7, I'm going to lower that to 0.3, which is realizing a Q much higher, around 6. I'm going to hit calculate, and now we see that once we reduce the damping in the speaker, we get a much higher response at resonance. One of the main features of Aries is an iteration feature where you can go in to your model and iterate on a parameter. For instance, let's say I want to iterate on the mass of the speaker cone. To the far right of that parameter is a button that has 3 dots in it. When I click on it, I'll go ahead and click on it, it solves the system for a variety of that parameter value. So if I go back to the graph element, we see the response of our system as the mass of the speaker cone is reduced for the red curve and increased for the blue curve. So you can see that the mass has a large effect above resonance. It affects resonance quite a bit, but at low frequencies below resonance, it's relatively insensitive. So typically what you'll use this iteration feature for is to identify what part of your model affects what frequencies, and then when you want to change the response of your model at those frequencies, you know which parameters that are that the model is sensitive to at those frequencies, and you'll target those in your design. Well, that is largely it. I hope this was instructive. Again, it was probably a little longer than an introduction should have been, but Aries is a large tool. It's got a lot of features, and I think you'll find it very useful for doing your acoustic design work if you choose to use it. Thank you for your time, and I'm going to wish you a good day.